Mass spectrometry is an instrumental method for determining the molecular mass of molecules. Knowing the mass of a particular molecule would be a pretty important piece of information to know when trying to deduce its structure. So the output of a mass spec experiment is what we call a mass spectrum, which is a plot of the relative intensity of different ions versus mass number. Okay, so here is an example, is a mass spectrum of pentane, C5H12. If you do the math, you will conclude that pentane has a molecular mass of 72. So the most important peak in this spectrum is the peak at 72. We call that the molecular ion because it has the mass of the intact molecule. So looking at this spectrum should bring two questions to mind. One is, why am I talking about ions when we're analyzing pentane, which is a neutral molecule? And second of all, if this is a spectrum of pentane, which it is, don't get me wrong, why are there so many peaks? Why not just a peak at 72? Don't we have pure pentane? Shouldn't it just have a peak at 72? Well, in order to answer these questions, we need to consider a little bit about how a mass spectrometer works. We're only going to figure out what we need to know in order to be able to answer these questions. I can go much, much deeper into the details of how a mass spectrometer works, but I'm not going to subject you to that at this time. So the basic principle is that if you take a charged particle and place it in a magnetic field, charged particles in magnetic fields travel through circular paths. Okay, that's a basic principle of physics, of electromagnetism that you can derive in any physics class, but I'm just giving it to you right now. And the radius of curvature, okay, whether it travels in a big circle or travels in a really small circle, depends on its mass to charge ratio. So depicted here is the diagram of what I'm going to call a classical mass spectrometer, which is also called a magnetic sector mass spectrometer. Any mass spectrometer has three important points. You have the ion source, which is on the left, the mass selector, which is in the middle, and the detector, which is on the right in this diagram. And as you can see, the mass selector, the magnet, is curved. So when you take ions and put them into the magnetic field, they're going to curve some amount to the left. So in a classical mass spectrometer, the mass selector is the magnet, and you can vary the magnetic field strength so that only ions with the proper mass, assuming they have one charge on them, will successfully navigate the curved path to the detector. Ions that are too light or too heavy will crash into one of the walls. They'll either have too big of a radius of curvature, in which case they'll just be going straight ahead instead of making the curve properly and crash into the far wall. And if otherwise, they will have too small of a radius of curvature and crash into the inner wall. That's a classical mass spectrometer. Many modern mass spectrometers actually use electric fields instead of magnetic fields to focus ions. So depicted here is the mass selector in what's called a quadrupole filter mass spectrometer, which is the most common type of mass spectrometer in use today. So you have a bunch of ions and they start to travel through the instrument. And instead of putting them into a magnetic field, the four poles, that's why it's called a quadrupole, have different voltages applied to them, and those voltages can be changed very easily. So electrons are going to be attracted to a positively charged electrode. They will be repelled from a negatively charged electrode. So if you continually change the positive and how negative the voltages are on the different electrodes, which is actually easier to do than changing magnetic field strength, you can select so that the ion that with the mass that you want will make it all the way through the maze, so to speak, get through the place in between the poles, and get through to the detector where it can be detected. Okay, so that's just for the information of people out there who may be interested in how these things actually work. So we now know that a mass spectrometer requires ions, because in all cases we're taking ions and either putting them through a magnetic field or through an electric field. So how do we ionize a stable organic molecule without changing its mass? Okay, we've already talked in class about ways that you can ionize a molecule. You could remove a hydrogen that is acidic. That will generate an ion. You can protonate a basic site. That will generate an ion. You can have a leaving group leave. That will generate an ion. But all of those processes will change the mass. Well, the answer is you take your molecule and you zap it with a beam of high energy electrons. When the molecule is exposed to this amount of energy, the highest energy electron is removed from the molecule to generate what's called a radical cation. What does that mean? Well, radical is something that has an unpaired electron, so it's going to be a radical because if you remove one electron from a molecule where all of the electrons are paired, either in bonds or lone pairs, there has to be an unpaired electron somewhere in your molecule. And it's a cation because if you remove an electron with its negative charge, you're going to leave a positive charge behind. Okay, another way to think about this, remember in general chemistry you talked about the concept of ionization energy for atoms. How much energy does it take to remove the easiest to remove electron? You know, a sodium atom has a very low ionization energy. It wants to give up its electron to generate an ion that has a closed shell, so it doesn't have that single electron in a new shell. Well, molecules have ionization energies also. And when you zap them with electrons, you're giving them the energy that they need to eject an electron and make an ion. And the energy that they receive in a mass spectrometer, which is typically 70 electron volts, is enough to ionize molecules in the same way that you can ionize atoms. So do we know exactly which electron is removed when a molecule is bombarded with a beam of electrons? In most cases, no. Do we care? Not really. Okay, we just know that it's losing an electron somewhere. Now, I've been talking a lot about electrons. I just want to make the explicit point not to get confused. We're using an electron beam as the energy source. The molecule ejects an electron to generate an ion. Those are different electrons. The only reason we're using a beam of electrons as the energy source is it's convenient. If we had some other way to give it that much energy, and there are actually other techniques that ionize molecules that are beyond the scope of this course, then those electrons will not be involved. But in all cases, an electron is going to get ejected from the molecule to generate a positively charged ion, or at least in all simple cases of mass spec. There are some ways in which you do add protons to basic sites and actually measure the mass of the molecule plus one. That's typically done in biological samples such as proteins. But that's a little bit beyond what we're going to talk about in this course, where we're talking about small organic molecules. Okay, so why don't we change the mass when we remove an electron? We've removed something, right? Doesn't that decrease the mass? Well, again, as you should probably remember from general chemistry, the mass of the electron is negligible compared to the mass of the proton or the neutron. So to the nearest mass or even unit, or even tenth of the mass unit, hundredth of the mass unit, whatever, the mass does not change from removing an electron. Then finally, if we're generating a radical cation, won't that be unstable? Don't electrons want to be paired? And haven't we spent several weeks talking about how unstable carbocations are? The answer is absolutely they will be unstable, and the consequences of that are going to be the subject of our next lesson. So stay tuned.